We're going to be looking at Unit 3 today, and I'm going to be going through the attached PowerPoint here to the topic list. Our main topic here today is really to talk about hardware and in technology, and I'm using this resource from a different textbook we use here at Gateway because I think they do such a beautiful job of explaining some of the fundamental precepts of hardware. This does come from another information systems book, by the way, and the topics that they talk about in this PowerPoint are these. I'll just let you read them really quickly, and then we'll get into what topics we'll go through in this PowerPoint. And some of this is kind of interesting because, you know, when you start to learn about IT, you hear a lot of people throwing terms around. They throw concepts around, they throw acronyms at you, and a lot of it almost seems like it's a challenge to see if, like, hey, let's see what you know, right? And I never want my students to kind of be left in the lurch. The first thing is you know, there's so much to learn about this stuff, even on the hardware level. There's no one person I've ever met that's been truly a savant expert in every possible area of IT. Although hardware, often I have met people that have reached that level because they focus so much on it. The focus of your program, of course, here in the data analytics program is not so much on the hardware, but you work so much with it in your profession that I think it's pretty critical to understand at least the fundamental precepts of it. And then, you know, it also helps you to understand what the limitations are or the possibilities are at the same time. So generally speaking, we look at hardware from the level of this concept that extends from information systems, system philosophy, basically. And there's this theme, and I know a couple of you are in my MIS class here too, but you'll see this like input, output, processing theme that kind of extends through all of IT, by the way, and all of information systems from both a philosophical and actual construction level of the whole technological world. Hardware is no exception, by the way. You know, these thoughts were kind of old in their foundation, but they're very logical when you start to break them down. So, typically speaking, a hardware system will typically include most of these components, and that is the CPU, which is the brain of the system, the primary storage, which we also call RAM, the secondary storage, typically a hard drive, flash drive, etc. Some way to input information and some way to output it. So a keyboard and a mouse, for example, might be input devices. Output devices might be your screen and your printer, for example. Most computer systems these days also, as a general rule, come with either wireless or wired communication technologies built in. And we consider that a standard component now. But there was a time ago that it was not standard, by the way. So adding a network card or a wireless card was always an add-on. And I find that fascinating, but now we consider that standard. In fact, I think a lot of us, when we're operating computers, don't even think that it's really a computer unless we're connecting to the outside world. It's like, what good is my mobile phone if I can't get online, right? Or what good is my laptop if I can't surf the internet? And we just expect that as a given. You know, the one thing that they talk about in this book a lot is, you know, strategic use of information systems and software and hardware systems. And, you know, there's kind of this thing that's been happening over time with technology. It's basically like this. The longer you wait, the cheaper it's going to get and the more powerful it's going to get. And that's always been true, right? And so I sit here today on this like 7-year-old laptop going, man, I think I want to upgrade. And then, you know, by the time I go out and upgrade, they'll come up with the next best thing, and it'll be even cheaper than what I just paid for. But at some point, you do have to dive in. The nice thing now is that for not really a lot of money, you can get a very, very powerful system. But I caution my students that if you are delving into buying something, research and shop around and get advice from people who know. Don't typically target real budget level computers if you plan to do professional level IT work. You usually want to get probably into like the the four-figure range usually to get a machine that's of decent quality that will last you a few years. That's my one general tip. All right, they talk about the hierarchy of computers, like from the top down, from the most powerful to seemingly the most insignificant. We talked during our Kahoot about supercomputers and how we had a company right here in Wisconsin called Cray that created some of the world's first supercomputers, by the way. But supercomputers are computers that typically are either one large device or many large, powerful devices working concurrently to simulate one computer system. Supercomputer systems are at the far upper echelon of computing, really owned and operated by very, very few companies. But things such as weather modeling or computing trajectories of complicated like space orbits and things like that sometimes require the number crunching capabilities of supercomputers in order to happen within a reasonable amount of time. So we see very few of these, by the way, and supercomputers often, they're not just like one device. They're usually like sometimes occupy a whole building, for example, kind of like ENIAC, but are significantly more powerful. What's more common is this thing perhaps known as a mainframe computer. And often a mainframe computer, like you look at this whole array of like technology here, and you might think of it as collectively as a mainframe, and that's not really the case. The mainframe might be like one box inside here, and all the other devices here are probably like storage and backup and auxiliary devices that go with it. So mainframe computers can often fit into something that's maybe the size of a refrigerator, in that range. There's also machines that are a little bit smaller, and they call them mini computers, even though they're pretty large. And this is an example of an old school mini computer, and this would be an example of more of a modern mini computer. And we call it a computer once again, but really it's a collection of devices working together to act as one computing device. And so it'll bridge memory and processing and all the other resources together. There's also another area of computing that we call microcomputing, and that's where we start to move away from the server level of things and start to think about what we use either in business or as individuals to complete work. And we call these typically microcomputers, or historically we've called them microcomputers. So that includes things like desktops, okay? Yes, an old school desktop, but here's a desktop. You notice what kind of drive this one has? You know what this is right here?
Cassette tape.
Yeah, it's a cassette tape. There was a time, believe it or not, in the past where we had companies where that was how you loaded your programs or saved your files. We had an old Tandy computer many, many years back that we were goofing around with that had a cassette tape drive. Fascinating that they would store their stuff that way. Most of us think more about desktops, and of course this is a very old Apple IIe desktop. This is very similar to the one I still own and is in the garage or somewhere in the attic probably. And desktops really started to come, into play basically late 70s and early 80s, and it kind of developed from there, into more modern machines. Like this would be an 80s IBM desktop. And then we think of maybe something like this that looks a little bit more modern. And this is probably like a 20-year-old machine here, by the way. But a desktop typically will have these components. So you have some sort of a box. It might be this big. It might not be. And then a keyboard and a mouse and a monitor. We do see a lot of like all-in-one units now too, where they take all the stuff that used to be in this box and they cram it into the monitor interface. That's a really popular format now. And I think it's a really cool one, actually, because then you don't have to like figure out where you're going to put this thing, right? So that would be a typical desktop. Now, if you guys work in corporate environments, not unusual, sometimes you encounter technologies like this, which is called the thin client. And let me explain what this is. Basically, a thin client refers to a level of computing where you will have a device on your desk that looks like a computer and behaves like a computer and even boots up like a regular computer. But when you get into the actual screens that you're using, you're really pulling down all the information over a network. You're not really operating the stuff inside this computer. The computer that's sitting in front of you is only there to allow you to connect to the server which runs the environment you're actually computing in. And so whatever you see on your screen might look like it's coming out of this box, but it's really coming from a server somewhere else. Thin client really refers to the connection technologies. And so on older thin client systems, you'd often see like these specialized boxes on the side that would then feed into the main system or into a monitor. Even here at Gateway, we have entire computer labs filled with basically thin clients where they're not really operating computers. The students aren't doing that. They're connecting to what we call virtual desktop interfaces, or VDIs, and they're just pulling all the the screen information to their station. And they have a keyboard and a mouse, but that's really being sent back to the server, and all the server is doing is feeding an image back to the screen. But that approach is not uncommon. If you guys, some of you I know have been at our main Racine campus when we were in normal operating paradigms, and if you guys know where my office is, there's a kind of like this little kiosk area where they have computers kind of on these curved walls that you can walk up to and use, and people would log in, check their email, submit their homework or whatever they're doing, and those were basically thin clients. They were VDI clients pushing out the information, so they weren't even real computers. Why did they do that? Because if somebody came along and let's say stole the little box that does the connection, they're not going to have anything. There's nothing inside that box, and the only way that box is going to work is if it's on the gateway network, right? And this box is significantly cheaper than buying the whole computer system. In many corporate environments, and some of you who already work in these environments will know this, when you sit down at your desk, you sit down, you seemingly have a normal computer, you log in, and then whatever you're getting on your screen you think is operating off of that computer, most often, and this is true at Gateway as well, most of our office workers operate through the VDI. They have custom Windows desktops that they have all their software loaded, all their access is loaded. It seems and behaves like a regular computer, but it's not really on their computer. And this is kind of the hardest one to kind of wrap your mind around, but on a corporate level, it makes a lot of sense. If you're pushing the computing resources through one central server, there's one upgrade to do, to upgrade everybody's desktop. There's one central point to do backups. There's one central point to scan for viruses, et cetera, et cetera. It's very convenient on a corporate level, so that's why many systems operate that way. The thing that's kind of fascinating is there's also this term fat client, which is the server that powers all of this stuff. So you can imagine that whatever computers you have in the middle that are pushing the screens out to maybe hundreds of users simultaneously have to be some pretty powerful machines and connected to pretty powerful networks in order to be able to move all that data around efficiently. And provided all your infrastructure is good, this can work for both remote and local users, by the way. But the fat client really refers to the server that powers all those technologies. So you do have to have something pretty robust here. Now, what most of us are using these days as our primary, I'll say, real computing platform is what we call a laptop or a notebook. And it was, probably about 15 years ago or so, where I think the threshold crossed that most people that are buying personal computers switched from buying desktops to laptops. And it makes sense. Why? Because with a laptop, you can fold up, put in your backpack, and go. Right? So you can take your work with you. You can take it to school. You can take it to work. You can take it to the beach. Well, don't take it to the beach. You should hang out on the beach. Don't compute on the beach. But you can do all those things and still have basically all the same power you have in a traditional desktop. Now, laptops do tend to cost a little bit more and don't tend to give you as good a performance as a desktop for the same amount of money, but the portability makes them worthwhile. Plus, you can operate on battery, which you can't typically do on a desktop. So, we've had this other rise of this category, and what's interesting is this author leaves the original name of it in place. What kind of device falls into the netbook category? Yeah, Chromebooks are the big one. And in fact, when somebody came out with this thought of a netbook, which is like a laptop but not quite as powerful, but still can kind of do all the same things. They called it a netbook. They didn't know how to really categorize it. And of course, Google has now taken it to the point where Chromebook is almost like a standard for like kids in K through 12 environments, and you know what, in a lot of corporate environments too. Because if you think about what most people do with a computer, it's typically this: they surf, they email, they do social media. I guess that's it. It's kind of like what the categories are, and there's not really much more. Okay, maybe they watch Netflix and play a game. And for most people, they can do that through a web browser. So why not just have a simple device that can connect to the internet and do those things without a significant cost attached to it? So you can get a Chromebook, like a really nice Chromebook, for a couple $100. And if you really want to drop the money and go up to like $300-400, you can get a really powerful one with basically the same capabilities. There are some distinct advantages. They're very, very easy to manage. However, you don't install software the same way. And in some cases, you don't even install software at all. Right? So if you're used to like installing software, what you do instead is you bring up maybe, if you're on a Chromebook, you just add apps to your browser, but they're not really on your machine. But hey, if you're doing the stuff you need, if you can email, surf, like things on Facebook, watch Netflix all through that device, what do you care, right? Well, for IT professionals, though, we cannot work on these devices. They are limited. There's a lot that we can do through a browser, but truly powerful work, especially development work, high-end data work, really does require a proper computer. And so unfortunately, even though this Chromebook, netbook category is exploding, it's not one for professionals, at least not yet. We'll see. If they can make better web-based tools that we could work with, where we can do our work remotely, we might see that change a little bit. I have had students, believe me, try to do some of my programming courses with a Chromebook, and I'm like, are you sure? Yeah, I can do this. And then like 2 weeks later, like, oh man, I need a computer. When they figure out they can't get it done on a netbook. All right. Another big category, which is really just a step down from the Chromebook. It's basically a Chromebook without a keyboard, or tablets. In many cases, you can install apps and stuff on these, but they're not quite in the same category as a Chromebook. I might even say that if I was given a choice between like an iPad and a Chromebook, I would go iPad, no doubt, because I can do a whole lot more with an iPad than I can do with a Chromebook. So we've here at home have owned many different brands of these. So we've done everything from like the Amazon tablets and Samsung and Apple and a few others, and often, they're like freebies or giveaways, like buy a phone, you get a tablet, that kind of thing. And my take on them is I think they're pretty darn useful in the capacity, like if you're doing the Chromebook-like things and don't want to be encumbered with the infrastructure of a laptop. So you don't really need that keyboard. So a tablet might be a better choice for you. It's also, in many ways, a good first computing device for people who are first being introduced to computing in general, because there's not really much they can screw up on them. And I don't know if you guys feel the same way about it, but for example, recently we hooked up internet for my elderly mother, who's in her late 80s, by the way. And her whole life she absolutely refused to use a computer. My dad did, she refused. But then we switched over her phone line, her landline, over to Time Warner or Spectrum or whatever it's called. And then she's like, oh, so my TV can get on the internet and I can watch YouTube on TV and watch all this cool stuff. And then she figured out, a tablet's kind of good too, because I can do the same, so now here she is, using a tablet and like her internet connected TV to actually get on the internet. And we feel okay with that because she really doesn't know how to compute, but there's not too much trouble she can get into on those devices, right? So that's one of the benefits of this level of, Chromebooks and tablets. Another area we should not ignore are what we call the wearables. And I don't know how many of you might own like an Apple Watch or a Fitbit or something like that, but this is a big growth area too. They were kind of booming. I remember like 5-6 years back. It's like I would just watch all the geeks in my classroom and be like, hey, check out my watch, man. Like everybody was buying the watches because they were brand new. I don't know if they're still quite as hot, but some people really like that because most of these wearables usually operate by tethering to your mobile phone. What I think is kind of interesting about this PowerPoint, though, is the author doesn't really have a separate slide for phones, but I think that's a huge mistake because I think phones, which kind of sit in between these two device levels, are really kind of in a category of their own. And for people in developing countries, by the way, I think we've talked about this too, phones tend to become their primary computing platform because, hey, if you can only buy one computing device, what are you going to buy if you're really only given the choice to buy one? And I think it's pretty logical to say for most people, a phone is probably the smartest choice because you can do stuff with the phone that you can't do with other things. With the biggest thing being is you can put it in your pocket and go, right? And a phone, in many ways, is more powerful than tablets and netbooks. And I have had students who have told me outright, I'm like, how did you put this paper together? Because it would be weird or something. And they would be like, oh, I typed it up on my phone. I'm like, well, no wonder. But it is possible to do. Absolutely possible to do it. All right. One other thing to talk about, because at some point you guys will be faced with this decision, or maybe you're thinking about it right now. I will tell you, I certainly am. So if we get another stimulus thing from the government, and that's probably where most of my money's going to go, by the way, either that or a sunny vacation somewhere. But you always have to think about what it is you're actually going to use that device for in order to decide what is appropriate for your level of purchase. And for people like you, right, especially as students, you may have had this decision even before you started school. And some students will rush out, take their money, even their financial aid money, and rush out and buy a laptop, try to get it purchased before the semester starts. And then they get to school, and then they see that their instructors will say, this is what you need, and it's not at all what they bought, right? And that might have happened to you. In some cases, it's almost better to wait and get some advice. But consider these questions and consider, that you get what you pay for as well. There are ways to compute and do high-level work without spending a lot of money, by the way. It's just a matter of how convenient you want it to be. Generally, most of us these days will opt to purchase a laptop more than any other device in order to do professional level work. But I will tell you that a desktop will always outperform a laptop no matter what. All right. I think this is a really good place to take a break, you guys. Let's do a 5-minute break and we'll come back and resume in 5 minutes. All right, we're back from break and we're going to continue on here with our progress. As soon as I click the right tool and set a zoom here. All right, the next section talks about some of the input and output technologies. This will go pretty quick, by the way. But when we think about input devices, and now I want you kind of to reflect back to our previous unit a little bit, where we talked about the topic being the human-computer interface and how we are kind of taking for granted now all the different ways that we can use input devices to connect with a computer. So interestingly, most of the typical things that we used or used to use to kind of move around on a screen, typically seen here, started with keyboards, then we threw the mouse into the mix, and then we got all sorts of alternate types of mice, including, like, for example, now, like, I'm touching my screen with my finger right now to get all the stuff that you see happening, that's happening with my finger because I have a touch screen. And that's a really big growth area. And the touch screen really made a lot of our technologies possible, including on our mobile devices such as phones and tablets, but very, very common on desktops and laptops now as well. The one platform that seems to kind of be either lagging behind intentionally or for some other reason is the Macintosh platform, where their laptops don't really have touchscreens, or they don't have touchscreens, but they do have touchscreens on their phones and their tablets, which always perplexed me a little bit. But Windows PCs now, almost as a rule, if you buy a brand new laptop, for example, you can almost count on the fact that it's touchscreen. And a lot of people really do like that, by the way. Has anybody here ever used a graphics tablet, like a Wacom tablet or anything like that? Okay. Okay. I know that very popular with artists. For example, I do own a couple of them, but my daughter tends to use them more than I do. But they're interesting ways to draw because if you draw with like a pencil, for example, you can use that surface to do a bunch of commands. Other types of input devices, things like these, joysticks and touch screens that we talked about, and digital pens, for example, that often work on top of graphics tablets, but sometimes you can get these digital pens that actually work independent of a tablet as well. Lots of input devices. We already talked about webcams and our voice, but we have other kind of devices too. So if you think about gesture-based input, and you guys will know what I mean, like if you've ever owned like a Wii game system, especially the old school ones where you had those like controllers and you could move them around, and you had like the sensor at the front of the room that would track your movements. And so like if you were playing baseball inside of Wii, you could swing the controller and swing the bat. And then of course, if you guys are familiar with the Xbox platform, Microsoft developed a kind of like a 3D imaging device that would recognize your body movements and translate that into game movements. And I think those are really profound devices and pretty advanced in many ways. Has anybody ever heard of this one, Leap Motion Controller? That one's a little more obscure, and it really strangely, I actually have one on my laptop. When I bought it, I didn't buy it for that reason. It just happened to come with it. But what it does is just this little infrared screen right next to my trackpad on my keyboard that projects an infrared field up into the air, recognizes my hand movement, if you guys can see me on the Zoom part here, and I could do things like twist or poke or pinch and all those things just in mid-air without touching the screen to control my computer. I think it kind of fell out of popularity pretty quick, but I still think they make the device, and it's really kind of a bizarre one to research because it's sort of related to the Microsoft, 3D Imaging Connect device, but it works off of a more localized transmitter. It was really designed for laptops. Very fascinating, and very bizarre to use, by the way. Other kind of weird input devices. So like we don't think of these things maybe as much. But when we walk into a store, we walk up to an ATM and we scan our cards. They have these like magnetic readers that read the strip on the back of our card, right? So we go to ATM or a point of sale machine. A lot of the modern card processing devices are using what we call embedded chips. So they use the chip readers to read the information off of your card. And I don't know if you guys are like me, but I also set up my mobile phone with my payment card. So when I walk up to like a point of sale device now, instead of putting my card in or swiping it, I just hold my phone near the, don't even have to touch it, just near the terminal, and it will read my card information that way. And a lot of people consider that a safer way to do transactions. Well, first, you don't have to touch that device that everybody else is touching. But secondly, when you use those pay systems, by the way, they generate pseudo card numbers. So the card number that's being used for the transaction is not actually your card number. So if somebody intercepts the transaction, they don't have your real card number. And it creates an extra layer of security. So that's true both for Apple Pay, Google Pay, and Samsung Pay all use that technology. And whenever you walk up to a point of sale system, by the way, and it says on the screen as an option, swipe, insert, or tap, the tap is where you hover your device. And I encourage you guys to try it out. It's pretty darn easy to use once you get it set up on your phone. I've been using it pretty heavily now during the pandemic, and I really like it. And now I try to use it every possible time I can, just as a general rule. Talk about some other devices here, some that are kind of older, including magnetic ink character readers. Does anybody know what this is for? Okay. It's okay that you don't know, but if you ever looked at a physical check, it has like these weird numbers printed at the bottom of the check with your account numbers and routing numbers. But what a lot of people don't know is those are actually encoded with magnetic ink. And there are readers that can read that information. And those are what we call Micr, or M-I-C-R readers. We also have the ability to look at characters on a screen or from a photograph or from a scan and convert them directly to characters. So that's OCR. That technology has been around a really long time, but now it is exceptionally good, by the way. There's all sorts of sensors and cameras. Here's another weird one that a lot of people don't know about, but is in use very heavily all around us. RFID chip is an interesting piece of technology because it's basically a computer chip that is passive. And what we mean by passive is it does not have power unto itself. So it doesn't have a battery, and you don't plug it into a wall or a power supply. It just receives electromagnetic frequencies through radio that activate it and then give us information. So one real popular use of RFID is this. If you guys have a dog or a cat that you probably have taken to the vet, there's a good chance that they're chipped. And what do they chip them with? RFID chips. These are passive chips. They inject it right into the pet, and that chip has the information about its owner, its name, its age, its shots, etc. And every time you go to your vet and they do the shots, they update the information into the chip if the chip is there. But RFID is in a lot more than you might think. There's RFID chips in our phones. There's RFID chips sometimes in our credit cards. Even more scary, there's RFID chips sometimes in our clothing. So for example, if you've ever gone to like the Gap or something and bought a sweater, right? There's a good chance that you maybe forgot to pay and walked out through the door and the alarms went off. And what's triggering that? And, sometimes you see that they attach sensors to the device, to the clothing. But in other times, they just build the chips right into the clothing. Right? So it's embedded into the garment or into the thing that you just bought. And I think it's kind of scary in a sense, too, because what happens with these chips? Well, hypothetically, if you pay, they deactivate them so you can walk out the door and not trigger the alarm. But the chip is still there. And some people who are really paranoid think, oh no, I got chips and everything, people are tracking me. And you know what? It's totally possible, folks. I just don't want to scare you, but yes, it's possible. And RFID is trackable even without power. So even if there's an RFID chip in your phone, which most of us have, by the way, you can pull out the battery, pull out the SIM card, smash the phone with a hammer, and as long as that chip's intact, it can still track your phone. And that's really kind of profound to think about. And RFID chips are anywhere. Companies like Walmart, for example, embed RFID chips into every pallet of product that comes into their store. And the moment that pallet crosses the threshold into the building, they have RFID readers that scan that pallet directly into the store inventory. No human intervention involved. Somebody stored it on the chip reads into the system, there's no error that can be made. A lot of companies are also making the move to get RFID chips embedded into everything they sell. Two companies that are really big on this, by the way, are Home Depot and Target. And what they're hoping for someday is that you'll be able to walk into their store, right? Throw the stuff in your cart and walk out the door. And it will automatically read all the stuff from the chips, charge your account automatically, and you're on your way. You don't have to stop and talk to anybody. You don't have to talk to a bagger or a checkout or any of that stuff. It's just all automatic. And that day, I think, is going to be here probably sooner than we think. And in many cases, they're already using this technology to do other sorts of tracking. Lots of different types of output devices, too. Probably the most significant type are monitors, the screens that we're looking at today. And we've gone through kind of like this whole revolution of like how devices are developed. We went through kind of like the old CRTs, which are the big, tube-powered monitors that were like, as deep as they were wide, typically. We moved up to LCDs, which are still in use, by the way, and a lot of our what we call LED screens, which most of these are these days. There are also flexible screens, right? So Samsung's like putting out phones that allow you, that have foldable screens, and that's kind of a mind bender that we even have that kind of technology. Other output devices very typically are printers. We have different types of printers. I'm hoping you guys are getting to the point where you're mostly paperless, but there's still things that you have to print on paper in many cases. So I think, these days, we own many printers here at home. I have lasers and inkjets. But I'll tell you, we very, very, very rarely use any of them, anybody in the house. And in fact, it's like, hey, I need to print something. Does that thing still work? It's kind of like that kind of thing. And I've been of the mindset ever since I've been actively teaching, which has been quite a long time now, that I would never accept anything on paper from any student ever, for as long as I've been teaching. And, thank God I taught in IT and people got that. But now it seems like the rest of the world's finally catching up to that, where you can do your legal documents now without having to print them on paper. And that's a big thing. Have you guys ever used like voice readers at all? Like had like Siri read you a book, or use the annotation feature that comes in Blackboard for that matter? This is kind of a thing too. Once again, a technology that's been around for a long time, but the voice readers now are actually working really pretty impressively. Let's move on to the CPU. We did our little Kahoot earlier, and we talked about the CPU. And one thing that I kind of learned a long time ago when I was studying computer science is that CPUs are in essence a giant calculator that are really only capable of performing one singular function. That singular function is addition. That's all they really truly know how to do, is to add one bit to another, from one memory location to another. The only other tasks that they know how to perform really are reading and writing to storage, and then performing that addition. And as a result of the extrapolation of those really super basic functions, on the most fundamental level, we have all the capabilities of a CPU. CPUs obviously these days have billions of transistors that are available, but the instructions that travel through those CPUs are always in a binary electronic format, so positive and negative voltages to indicate the ones and the zeros that are flowing through. The information travels through what they call a bus system to travel into the chip and through the chip. And then we also talked about the clock cycles and all that, and how every time a second strikes, the CPU is rated usually these days in gigahertz, and that's how many millions of operations happen per second on your system, on that really fundamental level. But that number being higher is going to mean a faster CPU and more quick operations of your machine. There's also other components to the CPUs that are, and actually this used to actually be an add-on back in the day. Like I remember when I bought my first 486 computer back in the early 90s, the math logic unit was an add-on, the math coprocessor they called it. So if I wanted my computer to be a little bit faster, I could buy that chip, throw it in. Now all the CPUs have that built in, but they actually have a separate little thing that helps with running the mathematical operations through the chip, and that's kind of fascinating. One thing that you guys may have heard of is this little construct here, Moore's Law, and I think that what works best on this one is to actually see it in a browser, because if I Google that, it's kind of like a famous little thing, and I think this graphic really kind of shows it pretty well if we can kind of get zoomed in here. And this is probably a good enough view. You can study this on your own. But there was this running theory that every 18 months, for a while, for a real long period of time, the projection was that we were doubling our capabilities with CPUs every 18 months. And that's been going on since, whenever this chart started, and I think they're probably starting in the 60s or 70s. And actually, they go back even farther. They go back to the analytical engine, the IBM machine, Colossus, Univac, blah, 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 all these superpower computers. And so far, we've been able to maintain this process of doubling our computer processing capability every 18 months. And every time they hit some sort of a physical wall of like the capability of the CPU, they find new and clever ways to circumvent it. And we have some really exciting advances happening right now in computing technology on the electronics level that have yet to come into the mainstream, that are poised to make this accelerate even further, by the way. And so most of our CPUs are built with transistors. They've, if you've ever studied electronics, you'll know that there's basically, I think, 3 or 4 fundamental components. One of them being transistors, resistors, capacitors, and I always forget what the last one is, but anyhow, those are some of the basics. What they came up with theoretically about 20 years ago was what they call the missing electronics component, which I'm trying to think of what they call it. It's not a transistor, not a resistor. It's a oh gosh, I forget the name of the thing, but it basically combines the capability of both a resistor and a transistor into one device. It's called a memristor, is what it's called. HP has been developing this for a while. They're the ones that first kind of did proof of concept on it, and others are latching on, by the way. But it's the capability that we do not have in our machines right now. We are close, because if you think about how you use a laptop, for example, when you're done computing, PC users often will shut down their machine. And why do they do that? Because they know what is in RAM is volatile and might go away when they shut down. Or if the computer crashes, they might lose what's in RAM, right? The memristor brings this to the table. The capability to have instant on with exact recall of exactly where you were. So the memory state would be maintained, and you would not need to boot a computer. You could power it off, take out the battery, disconnect the power supply, reconnect the power, and you'd come right back to where you were without having to boot again. And when this comes to the forefront, they're still working on the aspects of it. This will, I think, revolutionize electronics. And it will be promoted as the next best thing, but the reality is it's been built now for 20 years, and they're working on ways to try to make it available and affordable and, economical to produce. But I would see a point in time, maybe 10, 20 years down the road, that'll be the technology. And so can you imagine having a computer that's super powerful, even a server, and you just hit the button and it's instantly on and right back to where it was, and you don't have to worry about losing a thing. And that's one of the things coming down the line. The other big thing is superconductivity, which increases the rate of data transfer significantly, and the ability to build CPUs that go far beyond what we have now. So it'll be an exciting future, because computing capabilities are not going to diminish, folks. This curve doesn't necessarily seem to be slowing down. In fact, in some ways it seems to be accelerating. The affordability of it is a different aspect. It'll trickle down to the consumers a lot slower, but the capabilities are still increasing, and I think it's pretty exciting. All right, kind of moving down to computer memory, and this is probably one of the things that confuses people the most about computer systems, is the RAM on your machine. Now, one thing I always coach my students, especially when in these IT programs, is it's good to know how much RAM you have, and it always amazes me that so many people don't know. Now, you notice I opened up here my File Explorer, and I'm going to go to this PC icon, and I'm going to give it a right click and choose Properties. And the reason I'm doing this is I'm going to show you basically the Windows System Information screen. And on this screen, they list some of the fundamentals of your computer system, which operating system you're running, what processor you're running, and how much RAM you have installed. And the thing that I ask students to look at very closely are basically the 3 things that I pointed out. What version of Windows are you running? Are you running Windows 10 Home? And for most consumer machines, that's going to be a yes. And in some cases, it might be Windows 10 R, which is like what they put on netbooks or little devices, the budget machines. Where you really need to be as an IT pro, by the way, you really should be running Windows Professional, Enterprise, or Education, which are functionally equivalent, and give you some high-end features that are not available in the Home Edition of Windows. Does anybody know one feature that's available in Pro versions that's not available in consumer versions? Yeah, and a lot of people won't know this, and that's okay. The way that you know it is by needing the tool. Say that again, Cindy Lou?
It's not for networking, is it?
Nope, although it can be related to that. So one tool that comes in a Pro version is what we call remote desktop connection, which allows us to remote control other Windows computers. Both the ability to receive the control and to control something else. Another thing that's available in Pro versions is file and folder level encryption. So you can encrypt your files on your machine so that other people, even ones that know your login, can't see them. And then you can protect them that way. And those are just a couple samples, and there's much, much more actually, but those are the ones that people will use most often with the Pro level tools. There's also, kind of this thinking here that, if you have all these tools available, why not have them accessible? Now, most Windows 10 home users will be able to do most everything they need to do, including coding, without any limitations. But if you ever encounter the need for some of these higher level tools, that's when you will know that you need to upgrade. What I suggest to my IT students is, why not, since you have the ability here at Gateway to get a license for Windows 10 education for free, and I will show you that in just a few minutes, by the way, why not take advantage of that and upgrade your machine? What a lot of people don't know about Windows is that when you buy any Windows machine, and it comes with the home version, unbeknownst to the user, the other versions of Windows are already there. All you need is the license key to unlock it. And where do you change that? Right here on this button. So if you have a Pro license or a enterprise license or an education license, you can click here, enter the information in, a little bit of stuff that happens in the background, some unzipping or something, I'm not sure what it is, changing the registry probably mostly, and then those tools are unlocked in your machine. And by the way, since you guys are Gateway students, you get a license key for Windows 10 Education for free. So if you are running Windows 10 Home, I would encourage you to switch to the Education version. Okay, I think it's a really easy thing to do. Like I said, I will show you that in just a few minutes. The other thing I would implore you is to look at your processor and look at what type it is. And you can see mine's kind of old. I have a 4th generation i7, and it runs at 2.2 gigahertz. It's not the fastest thing on the block. You guys probably have a lot more than I do. But I do have 16 gigs of RAM, and so I have ample memory space to do most everything of what I need to do. All right, and I would say that those are kind of the 3 key things to look at here. If you are only at 4 gigabytes of RAM, I'm going to just give you a little bit of fair warning here. When you get to some of the upper level stuff that we do in the data program, your machine might be struggling and might not even function well. If you're coding in any way, shape, or form, it's usually good to be at least 8 gigs of RAM. And I would say the practical functional minimum these days, if I was buying a computer brand new, I would not touch anything that has less than 16 gigs of RAM. Wouldn't even consider it. And if you're maybe sitting at 8 gigs of RAM, which many consumer machines are at that level, major upgrade that you can do to improve performance is just to up your RAM. Get the RAM with the fastest clock speed that your system can support, and put in as much as you can afford to put in. Hopefully the maximum. Mine's maxed out at 16. But you will see that when you add more RAM, you're giving your operating system more room to operate, your applications more room to operate, and if you're filling your RAM when you're running at 8 gigs, you'll also notice a huge performance boost because now your machine's not writing to what we call virtual memory, which is a portion of your hard drive space that is reserved to act as memory to allow you to load programs that are bigger than what you normally can operate. Just adding the RAM eliminates a lot of that slowness and one of the single biggest performance boosts. The other one, of course, is that hard drive thing we were talking about before. So, for example, you can see on my machine, I have multiple drives, but yes, they're maxed out, and that's kind of embarrassing to show. But this one here is an SSD. It's a 500 gig SSD, and then I have my original drive sitting on my D drive. So this laptop here actually has 2 regular hard drive bays. And many of your laptops do too, and you might not know it. If they don't have 2 regular hard drive bays, chances are modern laptops will have a regular hard drive bay and then what we call an mSATA port as well. On this machine, I also have an mSATA port, so if I wanted to add a third hard drive, I could do that. Although at this point, I think it's probably wiser just to buy a new laptop. I mean, that's the point where I'm at. All right, but an SSD is a really big improvement too. All right, let's go back to the PowerPoint and finish this up. So when we talk about the memory capacity and the primary storage and the secondary storage, so the primary storage is our RAM. The secondary storage is our hard drive or any external drives. Whether it's a cloud drive, a flash drive, an external hard drive, a CD-ROM, a DVD, a Blu-ray, what have you. You can store your files. All of those are considered secondary storage. Primary storage in a computer, at least from the perspective of the CPU, is RAM. Interestingly, it is possible to actually take your RAM, declare part of it as a drive letter, and allow people to store files there. And your question might be, why on earth would you ever do that? Well, in the old days, if you were writing really big programs and you wanted really fast performance, we would do what we call RAM disk. So we take a part of RAM, convert it to a drive letter, save our files there. And why did we do that? Because we didn't have SSDs, but we could get that performance by writing to RAM. Of course, being really careful that you made sure you took any file in that RAM disk and saved it to a hard drive before you turn that machine off, because otherwise it's gone. Right? That's not really a technique we use much anymore, because now we have SSDs, which basically can operate as fast as RAM in some cases. And so, pretty fascinating little thing. Now, one little thing I want to throw in too about SSDs versus regular hard drives. If you do have a regular hard drive, they do have one advantage over an SSD, by the way. And that is, if they fail, if they crash and fail, a regular hard drive with the spinning metallic disks, you can actually extract data from ones that have completely failed. Where an SSD, if an SSD fails, it's a hard crash. You're pretty much not ever getting your data back. Also, on a regular hard drive, if you want to hide the information that you ever had on that drive, you can overwrite the sectors on the hard drive at least 35 times, right? I think is the minimum these days. And then data cannot be retrieved. On an SSD, you overwrite once, and that data is gone. It can never be retrieved. But that's kind of interesting about a traditional hard drive, and a lot of people don't know this. It's like, whew, I cleared my history and deleted all that bad stuff on my hard drive. Well, guess what? If you didn't overwrite those sectors on your hard drive 35 times, there's tools that can extract it, freely available tools on the internet that can do it. And so think about that as you work. But an SSD is not quite so friendly when you crash. So if you're using an SSD for your secondary storage, storing your files, make sure you always keep backups, because if your drive goes down, chances are you're not recovering that SSD information, by the way. That's one of the trade-offs. You get great speed, but almost zero recoverability. All right, let's talk about these terms. And we did that one Kahoot question where we were talking about the kilobytes and megabytes and gigabytes. And a bit is literally one piece of binary information. So for example, if I were to put a 1 or a 0 on the screen, one single character represents a bit. If I want to create a byte of information, I might have something like 011011100. And that's considered a byte of information. So 8 bits makes a byte. From there, the multiplier becomes the kilobyte, which is 1,024 bytes. Now, I can't put that on the screen, but you can imagine that's significantly more characters. And then every time we jump up this scale to each next level, the multiplier, so we multiply by 1,024 to get to the next level. So why 1,024? Well, it all has to do with the base 2 number system, because when we are working with bits and bytes, folks, you notice the only possible values are 1s and 0s. So with this single bit, I can only represent 2 numeric values, 0 or 1. With 8 bits, or a byte, I can represent 256 different values. And if you know the calculation there, what's really happening is every time I add a digit to the binary number system, I'm increasing its capability by a power of 2. So with 1 bit, it's 2 values. 2 bits, 4, 16, 32, 64, 128, and then finally 256. All powers of 2. And then if you extrapolate that out, the next level up is 1024. And then they use that to kind of leverage things. One little trick they do when you go out computer shopping, by the way, and you buy a hard drive, is sometimes they'll say, hey, it's a 500 gig drive, but really it's a 5,000, megabyte, which is not quite a gigabyte, because they're not multiplied by 124. It's a little trick they play. So you go out and you buy that 500 gig hard drive, and then you plug it into your computer, and it's like, wait, that's only 450 gig. What the heck? And you're wondering where those extra bits and bytes went. So you got to read the labels on those. But most of them are built that way. But it's all a factor of 124 or 1024 from here on up. So when you go kilobyte, you multiply by 1024, you have a megabyte. You multiply by 1024, you have a gigabyte, and then it goes up to. I'm trying to get my mouse to cooperate here. Then it goes up to terabyte, petabyte, exabyte, zettabyte, and I think they have even higher levels already declared. From a practical standpoint, when I hear like reports about storage and capacities and stuff, most people these days cap it at a petabyte, but you're hearing those words that, a little bit more and more that you've never heard before. And, a lot of people aren't aware of what they mean. But a terabyte's a huge amount of information, but a petabyte is really a huge amount of information. And as you go up, it's once again a factor of 1024, increasing up that scale. All right, we talked about primary memory, RAM, right? But there's actually 4 types, and that's what this little section is about. So part of it is what we call register memory. So some of that is built into your CPU and some of your chips. So some of the chips will have little storage spots built in that they can store things along the way, and those are called registers. Cache memory is very similar to register memory, except it sits adjacent to the chip and often stores instructions that are commonly used. So let's say, for example, if I launch Photoshop on my computer, right? The first time I try to launch it, I might wait like 10 seconds for it to completely come up, or 20 seconds if you have a slower machine. Close it, come back to it. Hey, it just came up in 2 seconds. How did that happen? Well, what happened is the launch code for it is embedded into cache memory somewhere so it can launch quicker. So stuff you do more often on your computer during a session will load quicker because you've already done it. And that's usually stored in some form of cache. Now, that's a really primitive explanation of cache because it really operates on a much higher level, but that's common that GPUs, CPUs, any other processing units on your machine will sometimes have a little buffer of memory to help with commonly used things. Even hard drives will often have cache memory attached to them, by the way. Random access memory, yes?
Referring to the cache memory, and I bring this up from some of our programming classes where we would, if we were developing a website, and we'd go out and test it to see, test our coding and stuff, and we'd go out onto to see it in Google or Safari or whatever platform, the web browser. Sometimes we wouldn't see our changes. We would always say, well, sometimes you have to clear your cache memory on that and like shut it down. And sometimes just shutting down the browser wouldn't fix it either. Is this kind of the same thing?
In conception, it's the same thing, but it's not. The kind of memory we're referring to here is embedded onto CPUs at a chip level. What you're referring to is on the software level. So for those of you that aren't web programmers, for example, so I'm just going to pull up like my Apollo launch page, and what a lot of people will do if they refresh a web page is they come up here and they click the button, right, and they reload. Or if you know the shortcut key of Control R, you can reload. What a lot of people don't know, though, is when web designers do work, for example, Sometimes you make a change to a web page and you put it on a server and you go to your browser and you hit refresh and it does. Look, I know the code's right. I made the change. I don't see the change. What happened? Right, Cindy Lou?
Yeah.
You guys know exactly what the web people know what I'm talking about. So then you learn that there's what we call a hard refresh. And these days, in order to trigger that in a browser, you either have to know the keystroke command or you do what I just did, which is right-click, inspect. You bring up this web developer tool panel. This is available in all major browsers, by the way. Chrome, Safari, Firefox, and Edge all have it. And then when you have this panel on, you can come up to your refresh button, click and hold, and notice how you're now presented with 3 different refresh options. And so you can do the normal reload, Control R, or the hard reload, which forces it to go back to the server to pull the page down. That's what that does. But despite that, most of our browsers still have automatic caching. So if there's images on the site or code on the site that's pretty complex, it will prefer to load it up from its browser cache, where it temporarily stores every page that you've looked at. And then if you just can't get it to refresh right, then you go to the last ditch attempt, which is empty my cache of all the stuff related to this page and reload it again for real. And then sometimes that's the one that allows you to see your work. And so sometimes, when we would do web design, and Cindy, you know what I'm talking about, we'd sit there and Control F5 like over and over and over again, and still nothing would happen.
Right.
And they didn't have this slick way of doing it back then. This is kind of like a last couple of years kind of thing. Right-click inspect, and then you have these more advanced reload options. And these are really handy. Usually you don't have to go past this one to make it work, but this one always makes it work. And if it doesn't work with that one, then you screwed up your code. But that cache is not the same thing as what we're talking about here. This is chip level cache. It's chip level cache, right? And now our regular memory on a computer usually will be in this category of RAM. That's like we boot up, and then we load programs, and then any program that's running will be loaded into RAM. Any file that we're working on is loaded into RAM until we hit save, and it writes back to the hard disk. The read-only memory, those are the special chips that we use on the system board, once again, that will store information even when the power is off. So it's kind of more like a flash drive or a solid-state hard drive. The problem with read-only memory, traditionally, it was always very expensive, so we didn't operate our whole computers that way because it would just cost too much money. But they would put little ROM chips onto the motherboards that would simply hold the basic information that would tell the computer system, hey, we got an i7 CPU, you got 16 gigs of RAM, here's your hard drive, here's your printer, here's your whatever, go ahead and boot. And mostly what it would tell the system is, as it was starting, is where to find the boot drive. That's like the main thing it would really be doing. It's like, hey, where's my instructions for booting? Oh, go to this one. Go to this thing. You can boot from C. C drive will boot you. But these are all considered primary storage in terms of the fact that the CPU, in most cases, can directly interface with all of these types of memory. And that's a pretty important distinction there too. When we talk about secondary storage, so what we typically think of as a hard drive, where we store our files or programs long term, usually fall into these categories. The solid state drives that a lot of us are using now, the SSDs, are right here. But in the old days, real old mainframe systems and even personal computers often use magnetic tape to record and store information. So if you see pictures of old mainframes, they have these giant refrigerator sized reel-to-reel tape decks that would be used to back up data and store stuff. Here's kind of a shocking thing. A lot of server level backups are still done on magnetic tape. And some people are like, why? Well, here's why. If a bomb drops and knocks out a server, but you have a backup on tape that you will not only put on the tape, but we're smart enough to take to a different location, now you can pull back all your stuff and rebuild the whole system. What a lot of people make the mistake of is they do backups, and their backups are in the same location with their primary equipment. Right? So, bomb drops, your location's gone, well, your backup's gone too. You know, now what people are doing instead of magnetic tape, though, most people that are wise are now backing up to the cloud somewhere, and a lot of us use like Google Drive or Dropbox or OneDrive or Box or SugarSync or any of those services where we can put files not only on our local machine, but also put them out in the cloud at the same time. That way, you know, like all my school files, for example, they're all on my Google Drive attached to work. Somebody steals my laptop or, you know, spills a soda into it, which has happened, by the way, and you lose your machine. I'm not losing any of my work for work because it's all out on my Google Drive. All I need to do is a new computer, connect up to it, I'm good to go. And that's something you have to think about. There are these other formats, though. So like the magnetic disks, strangely enough, refers to traditional hard drives because those metallic platters are still magnetically encoded. Very fascinating. Optical refers to what?
Like CDs?
Yep, CDs, DVDs, and Blu-rays. You know, and the reason they call them optical is like, once again, they're using a circular technology that works a lot like a record player, but they're reading and writing the information using a laser on the disk. And so it's done optically as opposed to magnetically. And that was seen as kind of like a panacea when it was first developed. In networking, we also use optical, data transmission on fiber optic lines, and that's something that we're starting to see now, even in the homes, even in our area. You know, if you get AT&T fiber optic service, for example, for your internet. So optical. Then we have flash memory, which is basically our flash drives, and it really is, related to SSDs. SSDs basically work on the same technology, by the way. Interesting thing is, they kind of close out this slideshow here with this like silly little table, and you see it kind of caps out at 2013. But if we could extrapolate that out to 2017, and they show like the technologies, the CPUs, the Pentium 2 back in 1997, and then by 2007 we were using dual core CPUs. So in other words, they would take two chips and put them on the same chip wafer in order to increase the capability of the chip, because what had happened really is they reached the limit of how much they could put on a chip. And so, all right, let's just use two of them, okay, and run them parallel. And then guess what? They did the same thing with quad core. Hitting the wall on the dual cores. Well, how can we make it faster? Well, let's go four. Okay, run those all together, and then you can increase your basically your data bandwidth and the amount of instructions that can push through the CPU at the same time. The astounding thing is now most of the cell phones that we carry are quad core. If you have like a relatively modern Samsung or Apple device, you can count on those CPUs being quad core, and in some cases even higher, right? So very, very interesting. The cost of them, of it, often more capability, lower or the same cost. This is really a pretty primitive chart. If you really did a study on it and did a comparison, you would see that trend continuing. One real fascinating thing, and I brought this up in my other class, and Dennis, I think you're the only one that was in that other class, is we have this thick thing going on right now where there's been, let me see if I can find it, if I can spell it right. Yeah, there's a problem that we're having right now with CPUs, and I shared this article in my Monday night class. But because of the pandemic, there's been a short supply of CPUs, and a lot of people who manufacture any sort of a device that requires computer chips is having a hard time getting their hands on them, and in many cases, it is shutting down production lines. So, for example, several U.S. automakers are having a hard time getting their hands on chips, and little did we know that you go out and you buy like a Ford Escape or something, and it's got like 20 or 30 CPUs in it. That's how many computer systems are in that car, and if you don't have the chips, you can't build a car, so it shuts down the whole production line. Over the holidays, I've heard that Apple in many places completely sold out of their products, iPhones, tablets, and laptops in particular. I didn't believe it. I walked into the Best Buy a couple of weeks ago, walked over to the Apple section, and I'm like, they don't even have display models, you know, and it's affecting things. So it might be kind of hard to get stuff for a while, and this might have a really huge impact on a lot of the things we do economically, especially people that rely on embedding these technologies in whatever they're manufacturing or using. So something that's kind of interesting, and the fact that they're calling it Chipageddon is kind of interesting, but they're talking about how, like, Samsung doesn't have enough chips for its phones, and they make chips, and they can't, you know, make them fast enough, and whatever. So the pretty significant thing that's happening in the CPU world right now, and something to keep your eye on ultimately. All right, this video will end here, folks.